Alright, so this one is about an LC circuit. In an LC circuit, we would have an inductor and a capacitor. Now, they didn't mention a resistor, actually. So we're just talking about an oscillating AC source, L stands for inductor, which is a coil. Okay. And then C stands for capacitor. So we'll have this. And we don't know the voltage of the source, but we do know the frequency is 57.3 hertz. They give a value for the inductance, and they give a value for the capacitance. Alright, we want to find the impedance at 57.3 hertz. So one option would be to use this formula, which says Z equals square root of R squared plus X squared. Alright, that's going to give you the magnitude of the impedance. But we know here the resistance is 0. And that X there is a little bit more complicated than it may look, because the X stands for the total reactance. It's actually not just inductive reactance and not just capacitive reactance. I mean, sometimes it is if you just have one or the other, like just one capacitor and no inductor, then it would stand for the capacitive reactance. But since we have both an inductor and a capacitor, we have to replace it with this expression, XL minus XC. See, it's actually a combination of both types of reactants. So we're going to definitely want to calculate both of those. So we want XC, which is 1 over 2 pi FC. Okay, so 1 over 2 pi times 57.3 times 4.8 E minus 6. Okay. Now, in addition to that, though, we're going to want to find the inductive reactance as well. So we'll have XL equals 2 pi FL. It's going to be 2 pi, 57.3, 3.2 times 10 to the minus 3. Alright, so we can see that in this situation, the capacitor really dominates the circuit because it has a huge reactance there, 579 ohms. The inductor is not contributing much at all to the reactance. Alright, but now we have to go on to find the impedance. Okay, so for that, we'll want to come back to this formula, and we'll just do, well, Z equals the square root R squared plus XL minus XC squared. The resistance is 0. Our inductive reactance 1.15. Capacitive reactance 579. Alright, so Z comes out to be in about 577 ohms. Alright, so now we want to vary the frequency and see how the frequency could really have an effect on the amount of current flow. So now let's let F equal 11,100 hertz. Alright, so our new XC will become this. Alright, and then we'll have a new inductive reactance. Where the frequency is 11,000. And 3.2 E minus 3. About 223 ohms. So our new impedance then will be square root of 0 squared plus 223 minus 0.033 basically 223 ohms. So the impedance in the one case is mainly due to the capacitor, whereas in the other case, it's mainly due to the inductor. So what's the difference? Well, the capacitor limits current when frequency is small. But the inductor limits current when the frequency is large. Now we just want to see what would happen if we were to introduce resistance into it as well. Then we'd be making what's called an RLC circuit. So let me sketch the new setup here. It'd be like that. We now have a resistor, an inductor, and a capacitor. Alright, we want to find the new impedance. So at low frequency, 57.3 hertz, we'll have Z equals the square root of now 34.6 ohms plus 1.15 minus 579. Okay. I get about 578 ohms for that. So the addition of the resistor didn't make a big difference because it was a fairly small resistance. At a larger frequency of 11,100 hertz, Z will be square root 34.6 squared plus 223 minus 0.033 squared. I get about 226 ohms for that. The last part says, compare the values of the impedance in parts A and B with those found in part C, where there was also a resistor, and why are they similar? Well, it turned out that the resistor's value wasn't large enough to make a big contribution to the total impedance. It certainly could have if it had been a larger resistance. We also find that at high frequencies, the inductor will dominate, but at low frequencies, the capacitor will dominate.